When we talk about energy in everyday life, we usually picture something like this: a marathon runner pushing through mile 22. We see someone with incredible stamina and endurance. Or we picture explosive, fast-moving power, two boxers trading heavy, rapid punches in the ring. We naturally associate energy with action, speed, and sweat. But in physics, the definition of energy is far more precise than human stamina or moving impacts. Energy is simply the capacity to do work. And work doesn't always look like motion. In fact, an object at absolute rest can possess a massive amount of energy, just waiting to be unleashed. Think of a drawn bowstring. It is pulled taut, quivering slightly, but it is completely stationary. Zoom out to the scale of the planet, and you find the exact same phenomenon. Deep underground, Earth's jagged tectonic plates lock together under immense pressure. They appear still, but they are loaded like compressed springs. This hidden capacity for action is called potential energy. It is energy stored entirely by virtue of an object's physical position or the configuration of a system. To understand how energy gets locked away like this, we need to scale down from tectonic plates to a simple everyday system. Imagine a steel ball resting on the ground. Now imagine reaching down, picking that ball up, and lifting it high into the air. To lift it, your muscles have to do physical work against the constant downward pull of Earth's gravity. Gravity is what physicists call a conservative force. This means the work you do against it isn't lost or wasted. Instead, it gets banked. We visualize this banked work as a ledger of gravitational potential energy, governed by the equation V of h equals mgh. The m is the object's mass, g is the downward acceleration of gravity, and h is the height lifted. Gravitational potential energy acts exactly like a perfect accounting ledger. It records the precise amount of work you put into lifting the ball, holding it in suspense until something changes. But this raises a question. If the ball is just sitting idle in the air, how does that stored energy know to pull it back down to the ground the moment you let go? The answer lies in the formal mathematical relationship between force and potential energy. The force acting on the ball equals the negative derivative of the potential energy with respect to height. In calculus, a derivative simply measures a rate of change. So this equation just means that force is the rate at which the potential energy changes with height. You can picture it as a steep spatial gradient or a physical slope. The negative sign is the crucial part. It dictates that the force is always directed downward, pushing the object to minimize its potential energy. Contrast this perfect storage system with a non-conservative force like friction. If you push a heavy block across a rough floor, the work you do is lost as heat. There is no gradient created and no energy banked to push the block back to where it started. Conservative forces are the only reason this energy ledger exists. They guarantee that the physical environment acts as a gradient, turning an object's position into a fully charged battery. To release the system, all you have to do is simply remove your hand, letting the invisible force of gravity take complete control. As the ball drops, its height decreases, and stored potential energy rapidly drains. But it doesn't disappear. It manifests as kinetic energy, the energy of motion. The kinetic energy bar fills at the exact rate the potential energy empties. Right before hitting the ground, the ball's height is 0, and its falling speed is maximized. We prove this mathematically by substituting maximum velocity into our kinetic energy formula. The equation balances perfectly. Final kinetic energy exactly equals initial potential energy. Physicists call this perfect transaction the conservation of mechanical energy. As long as only conservative forces are at play, the total sum of kinetic and potential energy remains entirely constant. This law governs the simple drop of a steel ball, but it scales up to the massive destructive forces we looked at earlier. When locked tectonic plates finally slip, it is exactly this same ledger balancing itself out, releasing centuries of stored potential energy into the surrounding Earth. The invisible concept of potential energy is nature's perfect battery. It stores physical work of the past